Okay, so this is where we left off. What did you decide? This is solutions part 2. Did you figure out that it was number 3? You did, great job. Okay, let's go on. We're going to use some problems here using percent mass. How many grams of sodium chloride are needed to prepare 250 grams of a 10% by mass NaCl solution? This is done oftentimes in the hospitals. So all we need to do is take that 250 grams and times it by 10%, and we've got 25 grams of NaCl that we need to weigh out. All right, try this molality problem. See if you can do it on your own. Given 25 grams of NaCl is dissolved in 5,000 milliliters of water, find the molality, remember that's moles per kilogram, of the resulting solution. See what you can do, pause it, and then start again. All right, let's check and see if you've got it right. First thing what we want to do is change the grams of NaCl to moles. So we're adding up a sodium and a chlorine, and that's where we get the 58.5, ending up with this many moles of NaCl. Next thing that we want to do is change the milliliters into kilograms. Since it's water, water's density is 1 gram per milliliter at standard conditions, so we can say that 5,000 milliliters is equal to 5,000 grams, which is 5 kilograms. We then take the NaCl and divide it by the 5 grams of water, and we've got our molality of salt water. Okay, now we're going to head into what's known as colligative properties. Colligative properties are things that happen when I add a solute to a solvent, to the solvent itself, how it's modified. Vapor pressure decreases. We're going to talk about each of these individually on the next slide, so don't worry about it. Just write down what happens. We have a melting point that decreases. We've got a boiling point that increases, and we have that osmosis is now possible because we have osmotic pressure. These all depend on the number of solute particles relative to the solvent particles and not the kind of solute particles. Okay, so when we're changing the freezing point, if we have pure water, it freezes at 0 degrees. We know that. We put in ethylene glycol, which is antifreeze, into our radiator so that it won't freeze at 0 degrees. It will freeze lower than what it would have frozen. So we look at our phase diagram. This is what actually is happening. Our melting point line is moving closer into the solids. Our boiling point line is moving into the gas area. That means our triple point has dropped. So we end up with a change in freezing point, and we end up in a change in boiling point. Okay, so now once we've got all that, our change in freezing point, it lowers the freezing point. So when we put salt on the road or sand on the road, it lowers the freezing point of water so that we don't get ice. When we put antifreeze in our car, it lowers the freezing point of the water so that we can run the car at lower temperatures. So here's some common freezing point depression things. We could use sand, rock salt, or ice melt to lower the freezing point and make it so we don't have ice on our roads. Sand is the cheapest, rock salt of course is next cheapest, and then ice melt of course is the most expensive. So as a city manager, you need to look at what one do I use and when. Sand will keep the roads ice free if it's not very cold. Rock salt is what I need to add to that to lower the freezing point if it starts getting colder. And ice melt is for the very, very coldest of cold winter days. When we add a solute to a solvent, it also changes the boiling point. We use this to boil water at a higher temperature so that when we make our macaroni and cheese, that our macaroni is not mushy. We also use it in our antifreeze so that we can run the cars at a higher temperature so that the water doesn't boil off. Here's the equation that we're going to use for both freezing point and boiling point. So boiling point is elevated and freezing point is depressed, meaning boiling point is going to get higher and freezing point is going to get lower. The K is a constant, so depending on what thing you're using, you're going to have a K. Depending on freezing point or boiling point, that's going to change. M is your molality. So you got to have the molality of the solution. And I is how many particles will that solute that I'm adding break into. This is called the Van Hoff factor, and we're going to practice it right here. So if I have glycol, glycol is a covalent molecule. It will break into one part. Sodium chloride is a ionic compound. How many parts do you think it will break into? How many ions? Did you guess 2? Good. How about calcium chloride? How many parts for calcium chloride? Well, if you get that there's 1 calcium and 2 chlorine ions, then you have 3. Okay, here comes a tricky one. See if you can do this one. Calcium phosphate. How many parts will it break into? Now you remember you're thinking ions. So polyatomic ions stay together. Here we're going to end up with 5 because we have 3 calciums and 2 phosphates. All right, so if you can do this, then all it is a matter of plugging in. We need to know the K's. We've got molality. Molality is moles per kilogram. We have to have a K. Here's some K's for some common substances. You are going to be responsible for water. So you need to make sure you write waters down, the KF for water and the KB for water. Now these numbers are in degrees Celsius divided by molal. So pause the video, make sure you write these down. Again, it's in degrees Celsius divided by molal as the unit. All right, so let's try some problems here. A change in boiling point. You can dissolve 62.1 grams of glycol, 1 mole, in 250 grams of water. What is the boiling point? Well, we already know what the molality is of this because we did it earlier in this PowerPoint. It is for molal. If we look at the chart that we just did on the past screen, or if we've written down, for water, the KB is 0.52 degrees Celsius per molal. Then all we have to do is plug in. The change in temperature for boiling point is going to be the KB times molality times I. Well, glycol I is 1 because it's a covalent molecule, and molality we already knew from earlier is 4.00. So all we now do is just plug in, and we get the change in boiling point. That's not our final answer. You need to be careful of that. Where does water usually boil? Well, it boils at 100 degrees, right? Well, we're boiling point elevating, so it's going to be above 100. So we add this number to 100, and we get the final boiling point. Pretty easy. All right, let's do another one. This is freezing point depression. Now we're going to go the other way. We're going to subtract it from the freezing point and get a lower freezing point. Same kind of thing. We just look up KF instead of KB. We have the molality of the solution. We plug in, the I for glycol is 1, and we get a freezing point of, our change in freezing point of 7.44. Where water freezes at 0, so we're going to go 0 minus 7.44, and we get a negative 7.44 degrees Celsius is the new freezing point. Okay, now here is one for you to try. So pause the video, try it, and let's come back and see how you did. We're back. We have NaCl. The NaCl will break into 2 parts, so your I here is 2. Your molality is 5.4, and your KF is the 1.86. We're going to plug that all in, times it out, we get 20.1. We're not finished. Subtract that from 0, and we get our new freezing point of a negative 20.1 degrees Celsius. How'd you do? Hopefully great. All right, let's talk about vapor pressure. Vapor pressure is going to lower when we add things to a solvent, and that's because of the intermolecular attraction. It makes it harder for the vapor to escape from a solution. The vapor pressure is lowered. So from the solvent alone to the solute, the vapor pressure is lowered. Next thing that we need to know how to do is mole fraction. Well, what's a fraction? If you take one piece of a pizza, it's a part or a fraction of the pizza. Well, same thing here. If I want to find the mole fraction of A, then I put the moles of A on top, and I divide it by the total moles that I'm working with. That's the mole fraction. Not hard. We use the mole fraction in a couple of applications. This first one is called Rayote's law. And Rayote's law helps me to understand what's going to happen to the pressure if my mole fraction is changed. So PA is the normal vapor pressure of A at that temperature. PA without the naught is what it's going to become. This is one of those times you want to make sure that you have the vapor pressure of the solvent, not the solute. We're not going to use it a lot. Henry's law is probably one that you realize but don't understand that you realize. S is solubility equal to some constant times pressure. When you have a soda bottle and you go and open it, what happens? It fizzes, right? Because the gas was under pressure, and because the gas was under pressure, it stayed in the solution. When you open the pop lid, the pressure is released or made smaller, and so the gas is allowed to come out of solution. So this is sort of like our ideal gas law. We're going to solve this for K, and we get solubility divided by pressure. So solubility 1 divided by pressure 1 equals solubility 2 divided by pressure 2. So you can find out what the new solubility of the gas is. You're usually working on gases here and not pressures, but you can solve for either one. This K is a constant, so we're solving for the constant just like we did in the gas laws where it was an R. All right, so just thinking about the pop, if it's under lots of pressure, gas is more soluble. Oh, excuse me. Okay, if we look at this chart, this is a chart of general solubilities of solids in a liquid. Most of them, as temperature goes up, increase in solubility. There are a few that are exothermic when they're mixed with water, and they actually become less soluble if you add heat. Gases always become less soluble as heat rises. Think of it. If you leave a pop out at room temperature, it becomes less bubbly. But if you store it in the fridge after you've opened it, it stays bubbly longer. Warm lakes have less O2 than cool lakes, so cool lakes are better for fish. So when we prepare a solution, sometimes we can't weigh out a solid. Sometimes we have a stock solution, and we have to use that stock solution to make other solutions. So we need to be able to dilute it. There's an equation for that. It's called the dilution equation, which is M1V1 equals M2V2. The capital M is molarity, moles per liter. Volume can be given in milliliters or liters. It doesn't matter as long as it's the same on both sides, because you're usually measuring out milliliters. If you want the units to cancel, if you're not solving for V, if you're solving for molarity, then you need to make sure the volume is in liters, so it will cancel with the liters in the molarity. Now, we're going on to the next thing, which is colloids. Colloids are suspensions. They're particles that are bigger than what would be in a solution, okay? But they're too small to be settled out by gravity. Again, they can be in all the phases, gas, liquid, and solid. You can look at a couple things. Here's a solvent-like and a solute-like, and what kind of colloid that it has, emulsion, foam, aerosol, and then see what we've got over here that's an example. Fog, probably all of you know, smoke, whipped cream, milk, marshmallows, butter. These are things that we have commonly in our life. Colloids exhibit what we call a Tyndall effect. This is a true solution. The particles are very, very small. This is a colloid. The colloid has bigger particles and diffracts the light. This is also an air colloid and an air colloid. As the light comes through it, it is dispersed. This is known as a Tyndall effect. Your headlights in the fog also give you a good Tyndall effect. Osmosis is the last thing we really need to talk about, and it's where some substances form semi-permeable membranes. This is what happens in your kidneys. Okay, it lets some things go through, but larger particles it blocks. We allow our body is sort of a filtering system. Okay, it's usually got a membrane of some sort. The higher concentration, the lower concentration of dilute flows into the higher concentration. We use the PV equals nRT. We rearrange it so N divided by V, which is molarity, is put into the equations. And we put, it's actually a capital pi, not the small letter pi, is equal to MRT, where M is molarity. And that is osmotic pressure. If the concentrations are the same, they're known as isotonic. And that's the end. So we'll see you in class.